All right. So, hello, Munich. Thanks, New4J, for having me here. And today I want to share with you our story of how we turned chemical reaction data with the help of a graph database, of course, into a powerful tool which supports different steps of synthesis process at Syngenta. So over the next half an hour, I will walk you through the surprises that we found in our data and the ontology and quality control gates, which we used to fix those surprises. As you can guess, they were not very pleasant. And of course, the open source tool, Noctis and Route Miner, which you can use yourself. And by the end of the half an hour, I hope that you will leave with a few ideas and some code how to make your own reaction data searchable, reliable, and insightful. So let me start with sharing a bit of my pain with you. So if you take a look at this cabinet, how does it make you feel? Imagine that you need to look for something in here. Frankly speaking, it gives me a bit of anxiety because this reminds me a lot the state of our reaction data before we started working on this project. So the information related to a single target can be scattered across different formats. It can be in tables, in reaction tables, or it can be in PDFs where chemistry is captured as images, and of course free text where chemists leave some notes why this reaction didn't work or how to do better reaction next time. So when data leaves like this, two things happen. So first of all, obvious, it's really hard to navigate this data efficiently, and maybe some pieces of information that you really want to know, you can't find them or you spend a lot of time. And second, you end up reinventing the work which you paid already for, and also the errors creep in. So just to give you some numbers, how big is actually this drawer? So first off, the sheer volume, if we sum together the number of reactions in some popular databases like Reaxys, CAS, Pistachio, it will be easily more than 200 millions of regarded reactions, and this number grows really fast every year. And what about formats? There are more than 40 different formats how reactions can be recorded. So you can imagine that it's quite hard to search, to do a uniform search across all the data at the same time. And there are duplicates both across the databases and within them. So there, and remember that as the automation is getting more and more spread, each high throughput robot can crank out around 1,000 of experiments in a week. So the drawer is not just big, it also grows really fast. And we need a representation that scales with this volume of data. And that brings us to the idea of treating every reaction actually as a part of network. This idea has been around for at least 10 years, and it's not us who came up with it, but here is the mental shift. So imagine instead of reaction string, you can actually represent reactions as two types of objects, a molecule nodes, the actual structures, and a single reaction node, the event that transforms these molecules into another molecule. So we can draw the arrows from molecule to reactant, from molecule to reaction, that molecule is a reactant to this reaction, and that reaction can have a product molecule. So applying this graph schema, we can actually create a small graph out of a single reaction string. So if we do this for all the reactions that we have, we can see that the reactions will be naturally connected through shared intermediates in a graph. So why does this matter? Chemists, they don't ask you question to show me reaction number 135. They want to know how can I get from a molecule A to molecule C by avoiding intermediate B because I don't like it. And this is what graph representation excels at. So if a graph can do a path what actually it unlocks for synthesis. So first, as I mentioned, because all the data is connected naturally to each other through chemistry logic, you can flawlessly do searches across different sources. Does it come from different labs or different patents? You don't care. In the graph, all this data is harmonized and easy to search all together. Then, of course, when you have a holistic view from the starting materials to your end target, you can run an end-to-end evaluation, which gives you a better understanding if you how to plan your synthesis. It gives you more tools to make your to strategize better, which doesn't mean that you will not make mistakes, but you will probably make less mistakes. And of course, also many valuable information can be found through graph through analytics powered by graphs. For example, show me the most common intermediate, or show me how many reactions failed for the synthetic tree. And last but not least, are AI readiness. So I think it resonates a lot with all of you, judging by how you voted at the poll. So when the data is connected and role validated, you can attach, for example, a language model which can ask the graph for, let's say, a two-step green route, and it will be a path with provenance and not a hallucination. So the bottom line, a graph isn't just a pretty storage format, but it's rather a decision engine for chemists, models, and managers. But only if the data inside is clean. So, and that's where we ran into trouble. So when I started working on this project, I was very excited to see how our internal data will look in a graph. And I was negatively shocked. So only 0.5% of data, of reaction data, which we were recording, was actually meaningful. It means that the rest didn't pass, I don't know, it didn't pass basic informatic validation, or it was missing some data, and etc. etc. So um, then I actually realized that we were sitting on a gold mine. There were 200 reactions which were creating products out of nothing. So, but unfortunately, it turned out to be data artifact. Um, and my biggest enemy is the ion of chlorine. If you run the analysis, what is the most frequent intermediate used in this project? It will be this guy. And it clogs all the searches, and it doesn't represent the chemistry that we are doing. So certainly these are something which has to be fixed. And after I did the role reassignment, for 67 reactions collapsed into 16 unique reactions. And the overall message from this analysis is that without strict roles and gatekeeper quality control, the nicest graph is still not useful graph, because the graph can connect, will just connect the garbage, but it will just connect it faster. It will not make it will not clean your data. Obviously, what you put inside will remain in the graph. So, and this was a call for us that we cannot go on like this, and we need to have a strict single ontology for every bench. And that's what we did. We have very strict role definitions, which are applied to any entry which goes through our synthesis tools. And the first thing is that we have a very clear definition of what is reactant and what is reagent. So reactant is a molecule which donates at least one atom to the product, and reagent it's the molecule which doesn't participate with any atom to the product. Think of solvent or base. And this is done automatically. It's enforced automatically by having on the background of our tools a reaction atom to atom mapping. So you cannot enter wrong data. And we went a step further with the products. We have expected products, among which there is a sub-role. The desired product, it's the molecule, which is the whole purpose, which was the whole purpose of this reaction. It's the molecule which we wanted to achieve in this reaction. The byproduct, it will be probably all the ions, or they will be labeled as a byproduct if they were part of cheminformatic representation. It's essentially expected but unwanted molecules. And the side product, it's a surprise guest, which maybe comes from some remainings of the previous step of reaction. So every bench, every entry goes through this ontology. And now what I showed you before, the ion of chlorine being the most connected intermediate is killed by this ontology. So now we have only relevant intermediates at the top of our list. But roles, it's not the whole story, it's just a half. We also need to map these roles into actual experiment which happens at the bench. That's why our ontology has multiple layers to it. So we start with the base representation, which has reactants and products. The next step is also having reagents, and it continues to the experiment where you can pin the metadata, temperature, the volume yield, who ran it, all operational information, and etc. And all of this is accumulated with a route. So we store the reactions not as an individual reactions anymore, but rather as sequences. And I will show you later why it's very important. So a route can reference to several experiments. So it references to all the reactions which are needed, which have been executed to get this target molecule. So why bother? The answer is very simple, is that now if you have a consistent ontology which links all the elements together, when a chemist runs a query for in cheminformatic representation, it can also fetch the system also fetches automatically all the experimental data relevant for this connected to this reactant and product. So how does this play a role in our real workflow? And so let's walk through it. How does it work? The synthesis design, chemists start with a synthesis design, and that's where they sketch the route in reactant and product representation. Then from the synthesis design tool, they pass it to the tracking tool, where they now can also add the reagents and prepare a plan for the synthesis execution. And at the synthesis execution level, that's where all the experimental data is collected and it's sent to a reaction data lake, which is a file-based database. So at every step, when the data is entered, there is a very strict validation, which is probably different from how chemists used to record their data, and they might see this as a downgrade, but what we give them back actually is that this connection, when the fetching, the search of real data to help design a better synthesis, to be more informed, to find the information which has been done in literature or in-house, this is much easier. Plus, now you don't need to look for a person who executed this reaction. All the data has been validated and we can trust this data. So, and of course, we also train retrosynthetic models on the data which we collect in the reaction data, in the reaction data lake, and we expose it in the synthesis design tool to our chemist. So, and I would like to invite you to have a look, to imagine yourself as a chemist at Syngenta. And I would like to show you how this tool actually works. So you start with a target. Here you can see different bonds where the molecule can break. And on the right-hand side, there are listed all the routes which are found for this molecule. So currently it's a retrosynthetic prediction, or it's a manual entry by a chemist. So you can filter, check some properties, and also you can apply filters for the intermediates. You can choose to show the routes which contain the starting materials which are available at Syngenta right now and you don't have to buy it. Or that, for example, you don't want to explode anything, hopefully, so you choose the starting materials which are not explosive. We have different graph representations which help to navigate the data. For example, you can collapse it by disconnections, by the bond which is cut during the reaction. You can unfold it and see what's inside. So every molecule has these little tags. And also you can not only do a single step away navigation, but you also can expand further by clicking at the molecule, and you can see what are the next steps. All the molecules are labeled. You can see straight away what are the starting materials, and also the instances of this reaction which have been executed in-house, information about the intermediates, their number, the source, and etc. etc. So you can, as I said, you can combine in this representation manual entries and retrosynthetic predictions. And or also, if you want, you can look at the whole graph from the beginning to the end. This is the depiction, or which reaches, which goes until it finds the starting material, and there are different kind of visualization which makes the image a bit more compact and readable. And Yeah, and also one can highlight different metrics computed from graph representation. For example, the most, the most frequent um, intermediates are in the synthetic tree. Yeah, so here it is. Yeah, so this is roughly how it looks like. It's also the representation which we hope will be adopted for brainstorming. So as you see, graph it really works well with reaction data. So you just saw a tool which combines two kinds of creativity side by side: manual entry and retrosynthetic predictions. But what is missing is actually navigation of actual experimental data. And that's why we are dropping here a graph, a Neo4j graph database. So this database is also going to be built from a reaction database, from reaction data lake, with the tool that we developed, Noctis. So what is Noctis? It's an open source Python package. You can pip install it yourself. It writes persistent Neo4j database. It has a customizable graph schema, graph queries, and analytics. With a simple YAML file, you can rename labels, define or new relationship types, and etc. We also implemented a custom route mining query, which I will talk about a little bit later. And also it has a data validation, or optionally, it uses similar tools which are used on the back end of our data validation pipeline across the workflow. And because we expect that people are going to use with large volumes of data, it's also possible to run the bulk import in parallel. So these are just the bullet points. Let's unfold them or what is behind them. So what do you need to create a graph database? It's actually, with Noctis, it's actually a CSV file which contains reaction strings. If you want to have a bulk upload, or you can also use or create it from a Python object. If it's, for example, your pet project and you want to run it in Jupyter Notebook, you can use a list of smiles or Pandas data frame. And then you need to define a graph schema. Or if you don't want to, if you want to use the base, if you're happy, you can also use the baseline graph schema defined in Noctis. And after that, the step 0 would be to have a Neo4j on your laptop, but assuming the context of the event, I guess that most of you have this already. So you just need to pip install Noctis and run these 3 lines of code to get your first reaction database on your laptop. So what about the performance is actually, I measured how much time it took me to run, to create a graph database from USPTO, which contains 500,000 reactions. And if you don't have any validation, then it takes 30, if you don't have any validation, it takes 5 minutes. And if you use validation, it would take 30 minutes with 20 workers. So the barrier to entry is really one file or one CSV file, one YAML, and 3 lines of code. So let's imagine that now we ran these commands and we have USPTO reactions living in graph. And I'm going to use an example of paracetamol. Hopefully none of you had to take it today. And I point Noctis to a paracetamol and I ask it to find all the reactions which are 4 steps away from paracetamol. And this will result into roughly 40 unique reactions. So for visualization purposes, here it's only shown 15. It's only up to 2 hops away. And it's very similar as a representation to what I showed you in our synthesis design tool. You can also run basic statistics on the fly. For example, I found 99 possible routes which have between 3 and 7 steps each, and 2 and 6 branches each. So we use this, we created this graph by using a curated by MIT subset of USPTO. And so all the reactions were atom to atom mapped. But still, if you zoom in, you can see that there are some strange things like this molecule is both product and reactant to this reaction, which once again, I think highlights the importance of not just having chemically correct data, but also having it correctly labeled. And still in seconds, we've gone from a collection of reactions into a panoramic map. That's how roughly we are going to have it also in our tools. And now I want to show you how we pulled out those 99 routes for the paracetamol. This is the job done by Noctis Route Miner. It's a Java jar that you literally can drop into your Neo4j plugin folder, no compilation, just copy, restart it, and done. It's ready to work. Although if you want to compile, you can git clone and compile. And if you prefer, you can use it through Python or also as a query in Neo4j browser. So what it does, it walks through the reaction trees and returns all the subgraphs which look like a route. So it's a chain of reactions that start from building blocks or stock materials and ends up at your target. You can set up the depth limit, stop label, and it actually pretty fast. It can extract in seconds up to 10,000 synthetic routes, but you should handle it with care because if your graph is hyperconnected or mislabeled, you can get stuck in combinatorial noise. So that's what was happening when we had ion of chlorine labeled as a product. And the bigger lesson to me is that the route miner enumerates all the possible routes, but it doesn't return you actual laboratory routes. So that's why you need to store them as a first-class object. And because it's important for model training to have a data set of routes for reproducibility and that's essentially what kind of data chemists are looking for. So, and another point I want to make is that when we were building Noctis, we were thinking about users, and it has a customizable graph schema, which you can define on top of the base schema through YAML or JSON. You don't need to recompile anything, or you can just add your YAML and run it straight away. Also, you can you can run any Cypher query, which you can run in Neo4j browser. You can run it in Noctis, and if you want also something fancy, you can mix and match Cypher and Python functions. And last but not least, any output of the query can be transformed into familiar outputs. So, for example, a plain list of smiles or network X graph or pandas data frame, you pick it. And so, yeah, with this, I wanted to conclude what is our dream workflow, what we are looking forward to do next. So today you saw that manual entry and reactivity model prediction already live together in a single tool using graph representation. And we are about to integrate also the graph navigation built from real data, so it's on the way. And this is our dream workflow and how we think graph should help everyday decisions. So the next ambitious step is to have a language model that can reason over the graph, so we can avoid the enumeration of the 10,000 routes for a target and instead pick the handful that matters right now. So we believe that having the ontology and the quality control gate and Noctis are the foundation to make this possible. So this is the roadmap this is our roadmap, and we are excited to travel it with the community. So that's the tour. And with this last slide, I would like to encourage you to check our GitHub repository, and if you scan the QR code, you will be redirected to our latest preprint, where you can find even more details about Noctis and route mining. And huge thanks to the people who made the work real, my colleagues and coworkers, Marco and Marta, and Guillaume Berton, whose support and leadership kept the wheels turning. We are also equally grateful to the Neo4j team for guidance and for the great engine under the hood. So that's it for me. Thanks for listening, and I'm happy to take your questions. If we don't have time, feel free to reach out via email or LinkedIn.